Hi Year 12. What we're looking at here is exercise 5H, applications of logarithms. But this little page here in front of me is not the same one that's in your booklet. We'll look at the booklet in a moment. I thought we'd start somewhere a little bit simpler and have a look at the example below. The example is asking us to find the equation of the normal to the curve, y equals log e of x squared plus 2 at the point x is equal to 1. Okay, so I've highlighted equation and normal because those are the two main things we want to do. We want to find the equation and it's going to be the normal. And we're going to use the rules that we've been using for calculus since last year and we're just going to apply those to logs. So we know when we're finding the equation, and our formula is y minus y1 equals mx minus x1. That's the formula we've been using for a year now. And we know our normal is perpendicular to our tangent. So we're going to use those bits of information and apply that to the log function here, and it's going to happen at the point x equals 1. So we're going to pop all that together. Okay, so we know our normal is perpendicular to our tangent, so we need to find our tangent. The gradient of our tangent we find by finding dy dx. Dy dx gives the gradient of the tangent. So what's our dy dx going to be? It's going to be our derivative on the function. So 2x on x squared plus 2. And that gradient of our tangent, which we could call m, that's what that is going to happen at the point x is equal to 1. So the gradient of our tangent, I'll put a little t there for tangent, is equal to 2 times 1, which is 2, over 1 squared, which is 1, plus 2, which is 3. So the gradient of our tangent is 2/3. Now that is going to help us find the gradient of our normal. So the gradient of our normal, do you remember what the equation is for that or how we work that out? The gradient of our normal is minus 1 and we flip over our gradient of our tangent. So what our normal is going to be minus 3 over 2. Okay, we're nearly there. So we've got our gradient of our normal, which we want to pop into the equation, and we need our x and y points. Now we've got our x value, okay, x is 1, but what happens to y when x is 1? Let's pop it back into here and find our y point. Y is going to be log e of 1 squared, which is 1, plus 2, which is 3. So log e of 3 or ln of 3, either way you can call it. Okay, back into our equation. So let's find, let's neaten that up there, the equation of the normal. I'm going to use our formula that we wrote up above for the equation of any line. So here's our x and y points. Y minus y1, I'm just going to write it as ln of 3, is equal to m. We want our gradient of our normal in this case, so it's minus 3 over 2. X minus our x point, which is 1. I am going to neaten that up a little bit. I'm thinking I might times everything by 2. So I get 2y minus 2 log of 3 is equal to, and I'm going to expand the 3 out, minus 3x plus 3. I can leave that like that. I kind of don't like looking at it like that. It does look very messy, but that is the correct answer. I might pop everything in general form and leave it all over to the left-hand side. Just because I particularly like the look of it that way. So I've left these two parts here and moved over the 3x and moved over the 3. Likewise, we could pop them on the other hand side, right hand side as well, and that would just flip the signs. Okay, I've just moved back over into our notes. So if you pull out our notes for this topic and look at 5H applications of the differentiation of log, you will find these in the notes. So I just want to talk about the curve a little bit first, and we're talking a little about the dominating component. But before we can talk about that, I think we need to draw a picture of what log e of x looks like. So I'll just draw my axes up there, and I'll get you to draw that in your books as well. X and y. I'll just change the colour. And we know that log looks like that. Okay, we know that it gets really close to here to the axis, and it goes through 1. So the notes over here explain basically what's happening as we approach x and infinity. So it says the value of log of x is large and negative when x goes to 0 from the positive side. So that's saying as x moves down the x-axis and gets towards 0, our log curve is moving very close to 0. It's negative, but it's getting very large. That will move down there and skim the asymptote, which is the y-axis. We're saying it grows very slowly beyond x equals 1. So once that log curve crosses our point here, 1, 0, it doesn't do what happens down here. It slowly grows, okay, because it's kind of turning as it goes. It's still increasing, but it's growing slowly. It's not growing as quick as, say, an x squared curve would grow. Okay, as such, it is not immediately clear what the limit of x log x would be as x goes towards 0. So it says in this instance, the x term dominates, and so we have the following limits. So anything times log of x as x goes to 0 is going to go to 0 as well. So here's our x log of x. The log of x is going to dominate, so as we get to 0, sorry, the x is going to dominate, not the log of x, sorry. That x term there is going to dominate. And so we're going to get closer to 0 as we have x log of x, as log of x itself is getting very large and negative. In the other instance, the x term is going to dominate as well, but as x goes to infinity, so as x goes the other way and gets large, we would have log of x over x going to 0. Okay, and we can verify that with some values placing in. Now, I wouldn't stress too much in that case whether or not you're grasping that. We're going to actually look at specific instances down here, and we're going to sketch the curve below and have a little look at this one. So we're going to sketch the graph of x log of x, but we're going to carry out these steps and see if we can actually sketch that. So the first thing wants us to have a look at the domain. So the domain of x log of x is happen to it what is happening up here. So x log of x is going to go to 0. So that means our graph is still going to be this side of the y-axis. So we're going to have values of x that are going to be greater than or equal to 0. Part B, testing whether a function is either even, odd, or neither. Great revision of this here, guys. So we're always popping in f of minus x. And if f of minus x equals f of x, we're even. If f of minus x equals minus f of x, we're odd. If either of those work, then we are neither even nor odd. Now our function is x log of x. So if we're popping in to find f of minus x, we're going to have minus x log of minus x, which is not even. So we're definitely not even. Does it equal minus f of x? So let's just have a look and see what f of x equaled. So that was at f of x, so they definitely don't equal there. But minus f of x pops a minus out the front of the whole function, so it doesn't equal that either. So it's neither even nor odd in that case. Part C. Okay, so part C wants us to find any zeros of the function and examine its sign. Now remembering, zeros are where a function cuts the x-axis, and something cuts the x-axis when y is equal to 0. So let's find when our function x log x is equal to 0. So there's two parts that can happen there. At x is 0, and when log of x is equal to 0, which we know is going to be 1. But in this case, if we didn't know that, we'd know, well, how do we write this as an exponential? We're going to say e to the 0 is equal to x, which is equal to 1. So there's our zeros. X is 0. Just underline that one. And x is 1. Okay, so let's examine the functions in part D as x goes to infinity and as x goes to minus infinity, noting any asymptotes. And we're looking at, see where that happens in terms of x log of x. And this is the bit that we generally, I think, as a whole, find quite difficult to visualize what's happening as x goes to infinity. But you can basically, if you're stuck on this, see what happens as you plot large numbers in your calculator. So as x goes to infinity, we're going to have a really large number in there for x, and we're going to have log of x going to infinity. Now we know as log, what happens as x goes to infinity in log of x. We'll just jump over and have a look at a graph of that. Okay, so I just jumped into Desmos there. So as x goes to infinity, and this is our graph of log of x, log of x slowly goes to infinity, doesn't it? So if we jump back into the OneNote and have a look at those pop together, so we're going to have x going to infinity as x goes to infinity, and log of x going to infinity a bit slower. So we're going to have y going to infinity as well as x goes to infinity. Now as x goes to negative infinity, let's see what happens there. So we need to think first of all individually what's going to happen to each of those particular parts of our function. So as x goes to minus infinity, let's think of what happens to log of x first. I'll jump back into our Desmos. So log of x cannot go into negative x values. So we can't have that happening. So as we're moving closer to 0, we don't actually get to 0 because we've got this y-axis being our asymptote. So we can't have it going to negative infinity. X gets to 0. And y equals x, well, that would itself go to negative infinity as y goes to infinity. So what we're going to have happen is y is going to go to 0 because we can't go past 0 in that case. So that helps us out a little bit. Let's see what our next bit is going to be. Oh, I actually forgot to mention on D, y is going to 0, but y is also a 0. So we're going to actually physically get to 0, and that's a point that we're going to stop at there. So let's look at E. And E would like us to find any stationary points and determine their nature. So we're thinking stationary points, that happens when our first derivative is equal to 0. So we need to differentiate this one first. We have a function and a function, so we need to use the product rule to do this. So I'm just going to pop that down there. So we would have u is equal to x, v is equal to log of x, u dash is equal to 1, I'm just going to squeeze that down there, v dash is equal to 1 over x. So using our product rule, we're going to multiply across those. We're going to have v du dx, which is going to be, let's call that y dash, ln of x, plus u dv dx, which is x over x, which is 1. So we're going to have log of x plus 1 is going to be our first derivative. But we want to find the stationary points, and stationary points happen when that first derivative equals 0. So we want ln of x plus 1 equal to 0. Log of x is equal to minus 1. So we need to find a value for x there. Remembering that ln of x, if you don't want to write it like that, it's still log of base e, and that might help you change this around a little bit. Log of base e, how can I write that as an exponential? That's written as e to the minus 1 is equal to x. So 1 over e would be an x value for our stationary point. Let's just move up here a little bit. So if x is 1 over e, what would y be? Y would be equal to x. Oops, sorry, not x, because x is 1 over e. Substituting it into our formula, we'd have 1 over e log of 1 over e, which would be equal to 1 over e log of e to the minus 1, which would be equal to, using our log laws, minus 1 over e log of e. So a stationary point is 1 over e minus 1 over e log of e. Actually go one more step there, I've missed it. Which is also 1 over e, and it's minus 1 over e log base e of e, which is just 1. So there's our stationary point there. 1 over e minus 1 over e. That was very long-winded, that one, wasn't it? And we need to determine their nature. We determine their nature by the second derivative. So let's see if we can find the second derivative. Our first derivative, y dash, is ln of x plus 1. I'll just zoom in there a little bit. So our y double dash is going to be the derivative of ln of x, which is 1 over x plus x. And we want to find the nature of the stationary point 1 over e minus 1 over e. And we know that, thinking back to our work on calculus before, if our second derivative is greater than 0, if it's positive, it's a happy one. If our second derivative is less than 0, it's negative, and it's a sad one. That's how we were thinking of it. And we're wanting to find that nature of that stationary point by testing our value of the stationary point, which we got as 1 over e minus 1 over e. So we're going to test it. So y double dash equals 1 over e plus 1 over e, which equals, if we flip that upside down, 1 over e is 1 times e over 1, which is e, plus 1 over e, which is positive, because this is a positive value and I'm adding to that, which is positive. So it is a minimum stationary point or a minimum turning point. Okay, and the last part wanted us to find any points of inflection and examine the concavity. So points of inflection happened when the second derivative was equal to 0 and there was a change in concavity. And that was for an inflection point. So let's have a look at that. Let's see what happens. If we pop our second derivative equal to 0, we got e plus 1 over e is equal to 0. So e is equal to minus 1 over e. Let us times both sides by e. So we're going to end up with e squared is equal to minus 1. And there's not going to be an inflection point because I cannot take the square root of a negative number. So no inflection point in this case. Okay, now let's go back and look at the question. Did we need to do anything else? I think we needed to graph it. Let's see if we can sketch that. I'm going to pop it up here. And we'll double check what we get with Desmos to see if we've got it right. It's not even, it's not odd. We know we're looking at a domain bigger than x, or for x is greater than or equal to 0, sorry. So it's hanging out in this part of our curve. We know we have stationary points at 0 and 1. We know that there is a, we'll look at this d in a second, but we know there's a stationary point at 1 over e and minus 1 over e. Now, 1 over e, I will be popping that on my calculator and seeing what 1 over e is. So if I pop that in my calculator, and I can definitely get a value for that, I end up with about 0.36 for 1 over e. So at 0.36, so a bit less than half, and minus 0.36, I'm going to get a turning point down here somewhere, and it is a minimum. So we're going to go like that, and I'm pretty sure we're going to go in like that as well. But let's now have a look and see what's happening here. As x goes to infinity, y goes to infinity. Okay, yep, so we're going up there. As x went to minus infinity, y goes to 0, so we're kind of moving up there. That's our graph. Let's jump into Desmos and have a look and see if we've got the right picture there. Oh, we're pretty close. I probably could have a little bit more of a turn on mine, but we're still going to infinity and we've got the right points in there. So that's that graph done.